This is a perfect Faro shuffle, or maybe Faro shuffle. You perfectly divide the deck in half, and then you perfectly alternate cards, right, left, right, left, right, left, interleaving the cards until your deck is shuffled. Let's watch it one more time. Perfect division in two. That bottom card is the right deck. There it is, and you can see perfectly interleaving shuffle. So what I want to know is, if I have n cards in the deck, let's assume it's an even number, and I do a perfect Faro shuffle over and over and over again on my same deck, how long until they're back in their original ordering? We might say right away that this is a big problem. So let's use our same solution strategy as before. Let's define a function. F of n gives the total shuffles to put n cards back in their original ordering. And then we can use our strategy of trying to describe that function by exploring small and simple examples. Well, I did that. I actually wrote a computer program to do it for me. So I had it create shuffles starting with a deck of size 2 going all the way to a deck of size 500, I believe. And here are the results, and what a function. So this is not like a function that I've ever seen before, that's for sure. And now I'm feeling less confident about my ability to find an exact equation that describes this crazy function. But I do notice something, and remember, problem solving is a lot about noticing and connecting to math you already know. So one thing I notice is this very strong, what seems like linear trend at the top. And then I'm also noticing at the bottom, if you look at the bottom, for some deck sizes, it takes very, very few shuffles to get them back in their original ordering. So as the deck size increases, you see these small dips down. And so what I'm wondering is, could I describe this upper bound, or could I describe this lower bound at all? Because even if I can't say, for 175 cards, exactly how many shuffles will it be, if I know an upper and a lower bound, I can say, well, I don't know what number it is, but it's definitely not smaller than this number, and it's definitely not bigger than that number. So it lets me put bounds on the range of possible values. Real quick, if you've never heard of upper or lower bounds before, I think the idea is pretty intuitive. For this course, I'll define it this way. If I have some unknown function f of x, you can describe any function you want g of x, and as long as it's always true that g is larger than f, we'll call it an upper bound. So you can think about it as a boundary where we're sure that f will never cross that boundary that's always above it. A lower bound you could define in the same way. You could have it be down here. Let's call this h of x. And as long as f is always larger than h, we would call it a lower bound. There can be lots and lots of different upper bounds and lower bounds, and they don't have to be linear. I could define a square root function like this. And as long as I'm sure that f never crosses my square root function, it would still count as an upper bound. For this class, I'm going to allow upper bounds to touch our function. So if we wanted to have it touch in one place, that would be okay as long as the function f never crosses. So once again, my question is this upper bound really linear, and can we describe an equation that is this upper bound? And my other question is it possible to make a linear lower bound? And in the actual question I asked you, I suggested that it was not possible, and I asked you to tell me why. Okay, so we're going to introduce two new strategies. Imagining what if something were true? What would you expect it to look like? What would you expect it to see? So if the bounds really were linear, what would you expect it to look like in the table, for example? And another strategy is to go back to definitions. What's the definition of the thing that you're interested in? So here we're looking at lower bounds and upper bounds. So being very precise in your thinking about what does it really mean to be a lower bound? What does it really mean to be an upper bound? All right, so let's do the upper bound first. It certainly looks linear here. What do I know about linear functions? I know that they have constant growth. So I think what I'm interested in is I want to try and look in the data table, try and pick out the points that I think lie along this upper boundary, and I want to check their growth and see if it really does seem to be linear. So let's look along let's look at the table and see which of these y values seem like they're probably along this upper bound. So I guess what I want to do if I'm looking at the y values is every single time I achieve a new highest y value, it seems like that's maybe going to be one of these points along the top. So this one here with a y value of 4, and then I see one at 6, and I see one at 10, and I see one at 12, and then this one at 18, and this one at 20. And I'm skipping these other ones because that's where the y values have kind of gone back down in between before the next largest. So then 28 is the next largest, and 36, and let's see, is there one? 52 right here. So now let's sort of pause there. And remember, it's all about noticing and connecting. So something that I'm noticing, and the pattern's not perfect in the ones that I've circled, but I'm noticing that the y values for a lot of these are 2 smaller than the x value. So 14 minus 2 is 12, 20 minus 2 is 18, 30 minus 2 is 28, 54 minus 2 is 52. So if this is the x value and this is the y value, most of the coordinate pairs that I've circled could be described this way. Take the x value, subtract 2, and there's the y value. So now I'm thinking, is this the upper bound? To decide whether that's true, let's go back to the definition. What does it mean to be an upper bound? So I said verbally that an upper bound is a function that your function never crosses, so never becomes larger than. So I guess my question is there any x value where the y value is larger than x minus 2? Because if it is, then I know, so you can imagine graphing this x minus 2 line. If I ever see a data pair where the x value is larger, where the y value is larger than the x value minus 2, then that would be a place where my function has crossed the x minus 2 line. And you can sort of scan in the data that we have and convince yourself that that never happens. So again, just like last time, we haven't actually proven that anything is true. We've collected a lot of observations, and we have a conjecture. We have a guess. And our educated guess is that this is an upper bound. In this case, proving that the number of shuffles required to return the cards to their original ordering never exceeds this feels like it's going to be a lot more difficult, but also maybe a lot more fun. So that's something that you could maybe think about. But this is what I was interested in you doing, was looking at all of this crazy information and thinking, what am I really looking for? I'm looking for the points along this upper boundary, and I'm going to check to see if they follow a pattern that's a linear one. Okay, let's look for points that are along this kind of lower boundary, these places where it dips way, way down. So one thing I'm noticing, okay, so I'm not sure here, but I'm seeing this 8, 3. Let's look for really small values. Here's a 4, 6 maybe, 5, 8 maybe, 6, 9 maybe, 8 maybe, 7. Okay, so if I'm looking at these patterns in the green, one thing that's popping out to me, so these ones that I marked maybe, I think maybe I'm going to exclude, because here I seem to be counting up 3, 4, 5, 6, 7. So I don't want to include this 6 because actually for a larger deck size, we get a smaller number of shuffles. So I don't think that this point that I marked as a question mark would be along kind of a lower boundary here. So let's just look at these. Oh, I'm noticing something else. I'm noticing that the number of cards here are powers of 2. I've got 8, 16, 32, 64, 128. So there is actually a function that describes these points exactly. You might not know what it is at this point in your math experience. But rather than try and describe what lower bound function this is, I want you to try and say, why can it not be linear? So let's try and give ourselves an easier to understand picture here. Let's clear away all of these extra data points and let's just plot the points from the table that we said were these ones that dip way, way down. So if these are my kind of minimum points, it seems like every single time the deck size doubles, the number of shuffles required goes up by 1. So you could imagine this is 1, 2, I'm just sort of very roughly plotting this here. That's 4, this would be 8, this would be 16, this would be 32 way out here. So each time I double the x value, the y value is going up by 1. So I'm getting this kind of curve here that's curving way out this way. You know what? Maybe this is going to be easier in Desmos. Okay, so here's what it looks like in Desmos. So again, I'm noticing that there's this curve here. And the question is, why can't I have a linear lower bound? So let's think about what a linear lower bound might be. Let's do 1 plus a times x. Let's have a be between 0 and 1. So, let's have it be, okay, just a times x. So let's sort of experiment. If I choose a linear lower bound with a slope of 0.2, for example, it's definitely a lower bound for these points, but you can see that these points here are underneath the purported lower bound, so it's not really a lower bound. So what if I make it even shallower, and so now I've got a new slope? Well, this new linear curve, this new linear function is a lower bound for all the ones that we have visualized here. But hopefully it's pretty obvious that if we kept plotting points, eventually these points would be smaller than our curve. Because what we know about a linear function is the growth is constant. The growth is always the same. And what I can see about this curve is that every single time I go up by 1, I'm doubling the length of the distance between my x points. So what that means is if you're going to plot the slope between any pair of points here, the slope is going to be getting smaller and smaller and smaller, approaching 0. So no matter how small a slope we choose for our linear function, the fact that the slope for this curve is getting smaller and smaller and smaller as we're going out means that eventually we're sure that the slope here is going to be so small that the linear function is going to cross our curve, which means that it's not a lower bound. So that brings us to the end of that homework problem. Hopefully you saw another illustration of making a table to see a pattern. But in this case, the pattern was very complicated, and so we had to be very clear about what we wanted to investigate, which part of it we wanted to see. So we said, what if it were really true that the upper bound were linear? And I had to select only the points that I thought would fit the pattern and see whether or not they really did fit a linear pattern. And when we were exploring the lower bound, I had to remind myself, what does it really mean to be a lower bound? And then again, zoom in on just the part of the problem that was relevant to the question I was asking, and then thinking about the growth. Thinking about, does the growth of my function mean that it's possible to have linear growth be a lower bound? And by thinking carefully about the growth, I was able to connect it to the math I knew and say that the answer is no. Interesting follow-ups for this question would be, maybe you do actually recognize the kind of pattern in the data that we saw, and you could find a nonlinear function to describe the lower bound here. That would be cool. Another thing you could do, there's a lot of interesting patterns in here. You see kind of strong linear relationships here and here. You could try and figure out what are those. You could try and find exact equations for certain kinds of input. There's a lot to be seen here. I actually spent an entire week with some freshmen one time exploring this problem fairly thoroughly. A lot of fun math in here. Good luck.